Hello and welcome to our first notes of the next unit, Unit 2, and this unit is all about random variables. We've been talking about randomness and sort of probability sort of every Monday, and this is going to talk about probability, but in a slightly different sort of setting here through thinking about like different variables and how we assign them, how we can find distributions involving those variables. And so the first one we're going to talk about is something called the discrete random variable. So first, since it's our first time talking about random variables, let us define what a random variable is. So a random variable should sort of remind you of like algebra and stuff like that. It is just sort of like this letter symbol that we use that assumes any of several different values that result in a random event, or like a probability event, something that's like you beforehand don't know what's going to happen. There's probabilities associated with these different outcomes, and thus it's random. And so for a discrete random variable, there's two different types of random variables we'll start our unit with here. So discrete versus continuous, you might remember that from algebra. So in a discrete variable, that's a variable that can only take on certain or distinct values. But we're dealing with numerical values here. But it only takes on certain values. It can't just take on like anything in a range. It's only some of the numbers in a range. So I have some examples here for us to sort of think about, which is three different sort of like games that you can sort of play. A lot of times these kind of result in games. So like Wordle is an example. I don't know if the kids are still playing the Wordle, but Wordle is an example of a discrete random variable. Why? Well, because the variable here is about how many guesses you get it in. You can get it in one guess or two guesses, three guesses, four guesses, five guesses, six guesses, or maybe you don't guess it at all. And then with each of those, you're sort of getting a probability associated with them, like as you've played a lot of times. So if you're someone who, has your first guess word has never gotten you a correct answer on that first word, you'd have 0%. Let's say you're maybe also not turbo good at guessing it on the second one. You've never gotten lucky and like almost made it work. But you're pretty good on the third guess. Your fourth guess is probably most often happening there at 42%. Of course, every once in a while it takes you a little bit longer, and it's five guesses. Ooh, the dreaded sixth guess there at 13%, and then there's been a few times that you have forgotten or not gotten it at all in those six guesses. So like those are probabilities that you could sort of associate with how many guesses it takes you. And there's no way to get like 2.5 guesses here. Nobody's ever been like, yeah, I got it in 2.5 guesses today. That doesn't make sense. It's only certain guesses or certain numbers on a range here. Raffle drawings too. I don't know if they still do those, but when I was a kid at, like high school games, they would have like a raffle. Go around with the raffle tickets. You buy it for $1. They throw it into a hat, and then at the end, they draw out a random raffle ticket. The winner takes home like half the pot, and the other half goes to something good, like, buying jerseys or charity or something like that. So in this case, you have sort of two examples here, two outcomes. You either win the raffle or you don't win it, you lose it. And let's say that 100 people bought tickets. And so if we're going like you win half of it, then that means like, hey, if you win, you get $50. But if you lose, you get nothing. And then like, what are the probabilities associated with all of that? Well, if it's 100 people, then you only bought one ticket, you got a 1 in 100 chance here, or a 1% chance, while you have a 99 out of 100 chance at losing. So you can see there we got like outcomes. Those outcomes have values associated with them and some probability. And then the last one I'll do here is the Roulette Wheel. The Roulette Wheel is a Vegas game. It's a big wheel with a bunch of numbers on it of different colors. And then they spin a ball around it. It falls into one of the little compartments, and you can win. There's a lot of different sort of probabilities and ways of thinking about it all. I'm going to go with the simplest one, which is that there are some numbers that are red on the wheel, and there are some numbers that are black, and then there are some numbers that are green. And so a common sort of bet you can make is like, hey, you bet on a particular color. And if it comes up that color, you get 1-to-1 odds on that. Meaning like if you put down $5, you win $5. So you walk away with $10 now. So let's say you do that. Let's say you're betting on red. And so if you win and it lands on red, you get $5. But if it lands on black, you get nothing. If you land on a green, that's nothing as well. And the reason this sort of works out well is because there's only a couple of greens on the wheel, and like almost half of them are red, almost half of them are black, but then there's these greens that sort of sway things. So as it turns out, there's 38 total numbers, but 18 of the 38 are red, 18 of the 38 are black, and 2 of the 38 are green. So you can see there that you have a slightly less than a 50% chance at getting red or black, depending on how you sort of bet. So yeah, but again, there's nothing in between. Red, black, green, these are only certain numbers. You can't win $2 in this game, you know. In the drawing for the raffle, you can't win $10. You can only win these certain values there. And that's what that sort of means. So we're going to go ahead and take a look at an example that's not a game here, and it has to do with life insurance. You know, not really something that you're too worried about yet, but it will be in the near future. So let's say that you have the life insurance policy. It costs you $50 for the year, but in the event that you die, it would pay $10,000 to your family, and if for some reason you were to become disabled, it would pay $5,000 to you. So in this particular scenario, our variable x is the value of the payout to the policyholder, or the policyholder's family in the event the policyholder perishes. So it's the value there. So, we can see it's $10,000, it's $5,000. We're not really worried about the $50 just yet. Or there's also an opportunity where there's no payouts, right? Because that would be if you stay alive or you are not disabled. So the possible values that we call x sub I and their probabilities that they occur form the probability model. So we're using this word model similar in the way we used it in algebra about how can you sort of define this with functions and values and things of that nature. So if we're thinking model, we're thinking that we're dealing with some sort of function. Not like a linear function necessarily or a quadratic function. There are different other functions that we'll be dealing with. And so that associates with a probability, it's a hard word, with each value of a discrete random variable. We denote that with the P, capital P, like we were talking about in our Monday lessons, equals capital X, which is representing the overall variable, and equal to these little x sub i's, these individual little outcomes that can occur in all of this. What's the payout for them? And then, as is the case for any probability space, the probabilities must sum to 1. If they don't, something bad has occurred here. So let's take a look at this example here. So we have these 3 outcomes here: death, disabled, or no change at all. So if somebody dies, then the policy says it pays out $10,000. If they become permanently disabled in that year, then it is $5,000. But if there's no change to any of that, there's no payouts. They will not give you just a couple of bucks for just staying alive. They give you nothing. So what are the probabilities in this? Well, it changes probably year to year. It changes insurance company to insurance company. So we're just going to go with a hypothetical here. Let's say that for our company, that in a year, we have only 1 out of 1,000 people that perish. So we're going to go with that. We have an insurance company here, and we only have 1,000 customers, 1,000 policyholders. So in a typical year, 1 of those 1,000 will die. In a typical year, we'll say that 2 people become permanently disabled, okay? So we got 2 people we got to pay out money to. And then The rest of them, though, are seeing no death, no disabledness. They are on the up and up here. Okay, so that's 997. So what we want to figure out first is, like, on average then, how much are we paying out to our clients, our customers, our policyholders every year? So I want you to try to think about, how would you calculate how, on average, how much we're paying out? So let's go ahead and do it. So the way we would do this is we're going to first figure out, well, in total, how much do we pay out? So that's pretty simple to come up with, which is that we have one person we need to pay $10,000 to, well, the family of that person, I suppose, because we have one death. We also have a couple of people who are disabled, so we're going to need to pay them each $5,000, which gets us another $10,000. And then we have 997 people who we pay nothing to because they're still alive. So that is the total amount paid out over the course of the year. That's $20,000. But we're talking about average, so we need to divide by the number of sort of like policy holders here. So we have 1,000 people under our policy. So when you do the math there, that is $20. So on average, we are paying out $20 per policyholder. Notice that that is not one of the possibilities in our payout column here. 10,000, 5,000, 0, not $20. That's because it's an average. So often with our discrete random variables, our average amounts here that we find, sort of like the center of our distributions, they are not actual values in our payouts. It's not possible to get $20 in payouts, but that's just an average. That's what an average sort of means for us. So another word for this is the word expected value. So the mean is the expected value. The average payout is the expected value. And so what this means is that it's sort of like a theoretical long-run mean value, center value for us, average value. So yeah, because of that, we can use it as sort of a measure of center for our model. So $20 is the center, which seems a little ludicrous because when you just look at the payout amounts, 10,000, 5,000, how could 20 possibly be in the middle? And it has to do with that weighting of the fact that there are 997 out of 1,000 people we're paying nothing to. So that's why it sort of skews so much that way in terms of the center being toward the $0 a lot more than our actual payout amounts. And so there's a formula here for us. E of x, that's the same thing as mu sub x, and then you can see it there. There's the sum of x sub 1s, so those are all of our payout amounts, times probability of x sub 1, so those are all those probabilities. So we got here sort of what's in our red column there and what's in our green column there. And so I reworked it out, sort of matching up with that there. You can see how it all works out to still be $20. All right. So another thing we want to talk about, if we're talking about center, is we probably also want to talk about spread. So I have filled in the table once again for us here, outcome, payout, probability. So why don't you take a moment to fill that out while I explain what we're going to calculate next, which is the deviation. That word should sound familiar. Standard deviation is something that we usually deal with, and we'll get there eventually. But what we want to talk about here is sort of how much do these payouts deviate from the actual mean value from all of this. So you can see here that we want to fill in this deviation column here, where we're going to take each x sub I, that's the payout, minus the mean. So for this first one, $10,000 is our payout. Our mean was $20. So the deviation here is $9,980. So go ahead and fill in the rest. So you should have gotten those other two values there. It's possible to have a negative deviation because we're just subtracting there. So now what we're going to do with these deviations is we are going to square them, okay? Why are we going to square them? Well, that's going to be sort of the difference between a particular value and the expected value. That's what deviation is, sorry. Why are we going to square them? Well, that's going to start getting us towards using these deviations to find our standard deviation. But we have a baby step in between. If we square all of these things, and then we find the expected value of those deviations, okay? In other words, remember that's coming back up here to this formula here. If we take all of those values, we multiply them by the probabilities of them happening, and then summing them up, we get something known as the variance of our distribution, variance. So you can see I've already put the formula here for us. So right here is our deviation from the purple column there. Meanwhile, the probability is still our green column there. So we're going to square those deviations, multiply by the probability. We're doing that 3 times because there's 3 outcomes. Sum it all up, and we get, that's this particular variance is, I'm going to write it over here, 149,600. What's our units in this case? Well, let's take a look. The units was dollars, and we're squaring them. So dollars squared. That's bananas and absurd. Who talks about dollars squared? The area of dollars? I guess you could do that if I was going to put out dollar bills to create an area. No, that's absolutely insane. We don't actually want to deal with variance as sort of a measure of center that makes, or sorry, spread, that makes sense to talk about in context. It is very important much later on when we're dealing with combining sort of different distributions. So like what if somebody had like life insurance, but there was like, you know, this particular policy pays out $10,000, but they have another one with a different company that pays out $200,000. That would be ways of sort of dealing with variance a little bit more closely, which we'll get to in the future. But for today, what we're going to do with this variance is we're going to go, great, I'm glad you exist. However, I'd like to switch over to standard deviation. And so when you switch over to standard deviation, we're just going to take this variance, and I don't know if you noticed, it is sigma squared there. So we're going to take it, and we're just going to take the square root of it. And that represents the average difference or distance of a random variable's value from its expected value, the mean, the center. Notice that that definition of standard deviation is not different from how we were using it before. It is on average how far our sort of data lies from the center, or in this case, our sort of different payout values, our outcomes, our values fall from the center or the expected value. So of course, when we do that here, so I have the formula for what is standard deviation. We take the square root of variance, and in this case, we came up with $386.78. So that's a little more in tune with what I would expect with the context. Dollars, not dollars squared. So you might be thinking, wait a minute, there's 3 formulas here. So I have to memorize all these formulas? Oh, be careful. Remember, we have a formula sheet in this course, and you'll be given a formula sheet for the AP test. And wouldn't you know, our first probability distribution in this table right here is discrete random variable. If we call it X, then here are the formulas for the mean and the standard deviation. And if you're like, oh, I'm sad, they didn't give me variance. Remember, variance is just the square of standard deviation. So variance of X is just the square of our standard deviation. So you don't have to worry about needing to memorize that. You just need to remember this fact that like the word variance means the square of standard deviation. All right, so let's go ahead and flick back over here, because you also might be thinking, that's a lot of number crunching. What if I had like 12 outcomes? I don't really want to do all this by hand. Is there a way your calculator can do this more quickly? Absolutely. Why don't we head over to our calculator and take a look? So let's take a look at how to use our calculator that will help us find the expected value and the standard deviation, and then thus the variance, of a discrete random variable. So in order to do this, we're going to go to our lists, so stat, and then just hit edit. And in list one, we're going to put all of our values in. So in this case, our payouts. So we're going to go $10,000, $5,000, and 0. And so normally with our sort of lists, it's like, oh, there's our data. We would just go to the one var stats, run it. There's our mean. There's our standard deviation. Problem here is that then that would be treating each of these values with equal weight. And based on our probabilities, we know that these are not all weighted equally. There's only a small chance of paying out $10,000 and a very large chance at paying out $0. So in order to make that work, actually, what we're going to do is we're going to move over to list 2, and we're going to put in the probabilities for each of these lined up accordingly. So $10,000 only has a 1 in 1,000 chance, or in other words, a 0.001 chance. $5,000 is 2 out of 1,000, so 0.002. And then 997 of our 1,000 are expected to have no change to their payout amount, so $0 there. All right, so now we have in our list 1, we have all of our outcomes, values, and then here we have all our outcome probabilities in there, so they're lined up with each other. That's really important, so you don't want to mix it up. So now we're going to go to our one var stats. So hit stats, click over to calc, that first one right there, one var stats. And here what we're going to do is we're going to put list 1 as our list, okay? And usually we leave frequency list blank because we don't have really frequencies. We want to treat every single item in our lists usually as equally weighted, as just a single thing. But here we want to actually weight them according to those probabilities. So for frequency list, put in list 2. And then you're going to go to calculate. And there you have it. We have our average there. X bar is 20. And then as you scroll on down further, you get to sigma, and that is 386.781. You know, we cut it off at 78 cents there. You'll notice it doesn't give you an S here, okay? So we're not dealing with sort of like a sample standard deviation. It's always going to give you sigma. And of course, if you're like, well, what's the variance of that? Well, the variance of that would be the square of this. So you could always just take that value and square it in order to come up with that. And the rest of this isn't that important. It tries to find, quartiles for you, which is not something that's very valuable for us. We're more interested in expected value up here at X bar and standard deviation here at sigma. So that's how you use your calculator. All right, so now that you know how to use the calculator, let's sort of summarize what we have discovered here for this single example. So basically, the insurance company can expect on average to pay out $20 with a standard deviation of about $386.78. That's a pretty big standard deviation. You notice that just moving standard deviation like 1 to the left of the $20 there is in the negatives. That's not good sort of things. And then ultimately, you can see that it also gets high really quickly. A couple standard deviations to the right of $20, and now you're almost in the thousands there. So like there's a lot of variability here, which kind of makes sense because there's like not a lot of payouts. The payouts are huge, but then they don't happen very often. And so there's like these things can swing a lot from year to year. This is why it's kind of risky business here to be an insurance company, and why maybe they charge quite a bit to sort of have you be a policyholder. So to sort of get us thinking about this, how these values can change and shift by quite a bit with just minute changes, let's look at 2 examples. So what if there was a natural disaster and 4 more people died that year than was expected, okay? So first off, what's that going to change? Think about it for a quick moment. So that's going to change the probability of death as well as no change. Those go hand in hand. So now instead of one person dying, we're going to have 5. And instead of 997 people surviving or not having any change to their health throughout the year, now we're going to have 4 less than that, so 993. So why don't you take a moment to try to come up with the expected value and the standard deviation using your calculator with this new scenario. And if you've already done that, why don't you move on to the next one? So what if there's a large accident that happens at a workplace that are all under your life insurance? And so now we got 10 more people who are on permanent disability than a typical year. Well, how's that going to change the expected value and standard deviation? So think about which values are going to change and which ones don't, okay? And calculate that. All right, so to finish up our video here, we got 2 things we're going to circle back to from the last unit: shifting and rescaling, or translating and dilating, or just scaling. There's a lot of different words that sort of mean this, but essentially what we're going to be thinking about here is like, what if I take sort of all of these values and I just add or subtract the same value to them for good reasons? Or what if I multiply or divide them by the same value for, again, good reasons? Like, how does that change sort of my distribution? Well, we know that like it doesn't change the shape of the distributions as we saw in the previous unit, but it does change centers and spreads. And so we need to think about that. So here we're going to talk about first shifting. So why would we shift this data? Well, I told you in the beginning that there was a $50 cost per year to the policyholders. So in reality, when we pay out $10,000 to a company or to a person because, or a family because somebody died, we didn't actually pay out $10,000 because we already got $50 from them. Obviously, that doesn't make a huge dent in things, but it will help us sort of understand how these things sort of work. And why maybe in the end we come out with a positive value, even though we had to pay out $10,000. So let's think about this. If we're dealing with somebody who died, yes, we have to pay them $10,000, but we already got $50 back from them. That means actually the only payout we have is $9,950. Disability, it's a $5,000 payout, but we got $50 from them. So that's going to be $4,950. That is a loss to us. And the last one, okay, or no change, well, we don't pay them anything, but they paid us $50. So we're actually not losing money here. This is a little confusing because it's a loss of -50. Well, that would be a gain. We actually gain $50 for every single one of these people. So what you should do now is take a moment and pause and find your expected value, and then take that and move it on over to the deviation column and fill that out and find variance and standard deviation by hand. I would really appreciate. And then you can use your calculator to check those. So now that you got that finished, by the way, don't worry about these boxes here. We will fill those in class and check on your work for those 3 things. We're going to do the last little bit, rescaling. All right, so what if we wanted to try to double our policy? Where we got 1,000 customers, or let's say we sort of slacked and we're losing customers. They don't really like it, so we're like, all right, we're going to double it. You die, your family gets $20,000, or if you go on disability, you get $10,000. So let's put that in. So we're doubling our payout here. We're not worried about the $50 for this example here. We're just worried about rescaling. But if you survive the year, no disability, we'll double your $0. You're welcome. So I'd like you to once again now come up with your expected value. Use that to help you fill in your deviation, and then find your variance and standard deviation after that. And then at the end of it all, I'd like you to sort of notice what things changed between shifting and rescaling, and how does that sort of fit what we already know about shifting and rescaling? And again, don't worry about these over here. We will fill those in as a class based on what you think you've noticed. So that's it for this video, okay? So when you come into class, we'll go over some of these blanks, talk about how to answer them. We'll work on your calculator maneuvers, and we will do some more discrete variable work together. See you in class.